When we first talked about the notion of function, we also talked about domain and range. And at that time, we were talking in terms of determining domain and range according to the equation we have before us. And we didn't really look at a graph. And it turns out that we can evaluate domain and range just by looking at the graph, and it's even much easier. Now, from before, you know, if we were looking at the function and determining domain and range, we would say, okay, what are the acceptable replacements for x here? And we'd say, well, let's see, radicals, we can only take the square root of positive numbers or 0. So x can take on only values which give us a radicand of 0 or positive numbers. And so x can be, let's see, -2 and greater than -2. So greater than or equal to -2 for the values of x for our domain. And then we go through and we analyze for range. Well, what kind of numbers do we get when we take the square root of these positive numbers or 0? What kind of numbers do we get out of that? What kind of numbers does y take on? F of x is y, you know. And so we determine that y can be 0 or any positive value. Okay, so from that kind of analysis, we can determine domain and range. But look how it's done graphically. We have a graph here. And instead of asking about the acceptable replacements for x, we're just asking ourselves, for what x values do we have positions on the graph? That is, for this x value, there is a y partner that puts a point on the graph. For this x value, there's a y partner that puts a point on the graph. For all of these x values, there is a y partner that put points onto the graph. Now, where does that begin and end? Well, it goes on forevermore in this direction, but over here, this x value doesn't have a y partner that puts a point on the graph. The graph stops right here. You see, so we're looking for the interval over which we have x values that have y partners that put points on the graph. And that interval begins here at -2 and goes out to infinity. So we could say the domain then would be from -2 to infinity, including the -2. And the range, well, to determine range graphically, again, it's much easier than using the equation. It turns out that we could just kind of shift our thinking from the x-axis to the y-axis. And we think, well, for what values of y do we have x partners that give us points on the graph? For this y value, we have an x partner that puts this point on the graph. For this y value, we have an x partner out here that puts a point on the graph. And for all of the y values up here, we have x partners that put points on the graph way out that way. But for y values down here, see, the graph doesn't go below the x-axis. And so for y values down here, we don't have partners that put points onto the graph. So we have no points for y values that are negative. The range then would be y values that are greater than or equal to 0. So our range then is from 0 to infinity. Here's another one. Now, this is a rather funny looking graph. It kind of it's just a segment of a graph or a piece of a graph, it kind of looks like. But first thing I'd like you to notice is this, that we have a point right here that's solid, and we have a curve, and then we have a point over here which is not solid. It's sort of not shaded in, and it just means that that last point on the graph is not included in this graph. Now, what about domain and range? Well, we don't have a function even to look at right here, but no matter, we can evaluate for domain and range. The domain is, let's see, over what interval of x values do we have points on the graph? Well, we have, for this x, we have a y partner that puts that point on the graph. For this x, a point on the graph. That x, a point on the graph. Back here, this x, a point on the graph. This x, a point on the graph down here. But for x's that lie out here, we have no points on the graph. For x's out here, we have no points on the graph. So the interval over which we have points on the graph are x values that are from -1 up here to 1, 2, 3, 4. From -1 to 4, but not even including the 4, because that point is not on the graph. So the interval for our domain is from -1 to 4, and not including the 4. All right, what about range? We just kind of twist our thinking a little bit. Now we're looking at the y-axis, and we're kind of looking across, you see, in order to decide the interval along the y-axis that gives us points on the graph. Well, let's see, down here, we don't have any points on the graph down in this neighborhood. So, but we start here at a y of negative, let's see, 1, 2, 3, 4, 5. At negative 5, we have a spot on the graph. And then up here, we're thinking horizontally now, and we have a spot all the way up here at 1, 2, 3, 4. You see that's on the graph, but none up here. So the interval along the y number line that gives us points on the graph would be from negative 5 up to 4. So the range is from negative 5 to 4, and including those endpoints. Now we can also evaluate in a way that's not too different from our evaluation algebraically. We can evaluate functions graphically like this. F of negative 1 means on the f function, and here's its graph, replace x with negative 1 and evaluate, or find the y value for this value of x. F of negative 1, that's what that means. When x is negative 1, the y value is negative 1, 2, 3, 4, 5. So f of negative 1 is negative 5. F of 2 on the f function. When x is 2, what's y? When x is 1, 2, y is 1, 2, 3, 4. F of 3 means, let's see, when x is 3, y is 1, 2, 3. F of 3 turns out to be 3. Another question that might be posed is, for what values will f of x be equal to 0? Wow, for what values of x will f of x be equal to 0? Now f of x is the same as y, so it's saying that for what values of x would y, the vertical distance, be equal to 0? Well, that happens right here. You see, that happens right here at the origin. Now that's nothing but an x-intercept. For f of x to be 0, that means y is equal to 0. And we have a 0 then at x equals 0. Now if this were solid, we would have two zeros. I'll make it solid here just for the discussion, but it is that a 0 means for what value of x is the y value equal to 0? So that happens at the x-intercepts. So the zeros are at the x-intercepts, and the x-intercepts are at x equals 0 and x equals 4. Zeros are x equals 0 and x equals 4. Now I'm emphasizing the idea that zeros are values of x, but they are values of x that give us x-intercepts. X-intercepts and zeros then mean exactly the same thing. Suppose we want to find the zeros of this function. Now the zeros in this, this algebraic notation, in this function notation, not graphically, it's exactly the same idea. It's the values of x such that f of x is equal to 0. That is, we want the values of x that will cause this expression to be equal to 0. So we do this. You see, and we solve for x in this equation. Now graphically, we could do this. We could use the graphing calculator. We could just say, okay, let's let 0 be replaced with y and put this onto the calculator and then find the places on the graph where y is equal to 0. You see, then we're finding the zeros. We're finding the x-intercepts. Same idea. All right, let's do it algebraically. Now, algebraically, we know to solve this. It's a quadratic equation, so to solve it, we're looking to factor. So we would write, let's see, probably the 3x times x combination for 3x squared. The last sign is negative, so we want the plus minus combination. If I just pop in a combination like this and experiment a little bit, I'll fish my way through it. 10, factors of 10 are probably 5 times 2. I'm going to put the 5 here, the 2 here. Now let's see, I have 5x here. I have negative 2 times 3x, that's negative 6x. But negative 6x plus 5x would be negative x. But I want plus x for the middle term. So I need to swap the signs. I'll make this plus and this minus. And now we have minus 5x plus 6x. That's plus 1x, and the factorization is correct. Now, to identify the zeros, we identify the values of x that will cause each factor to become 0. This one's pretty obvious. We know that x would need to be negative 2 for this factor to become 0. But it's not so obvious here. And so we would want to write a little linear equation. I don't quite have enough room right here, so I would slide out to the side maybe and do something like this. Say I would like to find the value of x that will cause 3x minus 5 to be equal to 0. And then solve this. I would find, let's see, adding 5 on both sides and then dividing by 3. I find x to be 5 over 3. Let's slide this over here. So x then is 5/3, our two zeros of that function. Here again, we want to find the zeros of this function. We just set that expression equal to 0 and solve it. Remember, our prescription for solving an equation involving a radical means that we undo the radical by performing the inverse operation. We see square rooting, we square on both sides. Square over here, we get 0. Square over here, we get the radicand. Now I'd like to separate these two. I'm noticing that I've got a quadratic equation here, but it's a pretty easy one because I have no first degree x. And in that circumstance, I can use this square root property, recall. So this is x squared equals 10. And so I know that x is equal to plus or minus the square root of 10. So we get two irrational values for our zeros in this function. Let's get back to the idea of whether or not we have a function. And making that decision, we can either evaluate algebraically or graphically. And it turns out that the graphical evaluation is easier than the algebraic evaluation. You know, algebraically, what we have to do is decide whether or not our equation meets the definition of function. Now that means that is it the case that for every value that x can take on, for every value in the domain, is there exactly one value for y? You see, and so we would have to look at that algebraically. Let's take an example. In this equation, if we're evaluating whether or not this is a function, we say, is it the case that for every value that x can take on, do we get exactly one value for y? Yes, that does turn out to be the case. But it's even easier to evaluate it graphically. It is for each x value in the domain of this function, do we have only one y partner? For this x, one y partner. For that x, one y partner. For this x, one y partner. For that x, one y partner. For this x, one y partner. For every x in the domain, we have exactly one y. It meets the definition of function. So here we have the graph of a function. Now what about for this? Now algebraically and graphically. All right, algebraically, we can evaluate kind of like this. We might come out to the side and solve the rascal for y, and we can see it very clearly. Now, I think we looked at something like this before, but if I add 2 on both sides, I have x plus 2 equals y squared. And then y then is plus or minus the square root of x plus 2. So the idea is that x can take on a single value and y will take on two values. So when x is, let's say 7, for an x of 7, we would have 7 plus 2, 9, the square root of 9, 3, plus or minus 3. So y is plus or minus 3. And that means one value of x is giving rise to two values of y, not a function relationship here. All right, now graphically we can see it more clearly, or as clearly, I guess, but much faster. And it's evaluated like this. For this value of x, we have two values of y that place points on the graph. You see, so for one value of x, we have two values of y that put points on the graph, and that's all there is to it. Now, this idea of a single value of x putting two values of y, or associated with two values of y for points on the graph, gives us a way to make this test for functionality like this. It's called the vertical line test, because it turns out that if we can imagine a vertical line intersecting the graph, and if that vertical line intersects the graph in more than one point, then we have that condition where one x is associated with two y's. You see, and so we don't have a function. Now, if a vertical line anywhere in the domain of the function intersects in only one place, like here, you see, I'm performing the vertical line test. Now you do this mentally, you don't actually draw the lines, but it's the idea that you imagine vertical lines, and if they intersect the graph at only one point, then you have a function. If the vertical line intersects in more than one point, then you don't have a function. Let's evaluate some others. We have a kind of a curvy looking graph here. I'm looking at it like this, evaluating it with a vertical line test, and every vertical line intersects the graph in only one spot, so this is the graph of a function. Now what about for this one? Well, it passes a vertical line test over here in this part of the domain, but it fails a vertical line test here, and therefore this is not the graph of a function. Here also is a situation where we pass the vertical line test in one part of the domain of the function, but we fail the vertical line test here, and so this is not the graph of a function. Now here we have a curvy graph, but it passes the vertical line test, and therefore this is the graph of a function. Now when graphs become more and more curvy, there are descriptions of the graph that help us understand the behavior of graphs a little bit better. And one notion is the idea of increasing and decreasing and perhaps constant. Now let's move back over here, and I want to show you a situation, or several situations. Our first graph over here was one which was increasing over the entire domain of the function, where our graph is starting here and it's continually increasing. So this is an increasing function. Now this one is not increasing over its entire domain. It's actually increasing over part of the domain and decreasing over another part. And a lot of times this increasing decreasing idea is one which is sort of separated into intervals. And here's what I'm talking about. Now just for emphasis, I want to do this, that I'm thinking of an interval along the x-axis. So within this interval on the x-axis, the graph is increasing. And within this interval, it is decreasing. So it's the idea that from -1 to 2, and you do it like this, from -1 to 2, it is increasing. And from 2 to 4, it is decreasing. Now, there are certain circumstances where a graph might go to a certain point like this and then stop and then just kind of go straight. And in the interval where it kind of goes straight like this, and maybe it'll continue up, maybe down, whatever. But in this interval, it would be said to be constant. So it's constant over a particular interval in this circumstance. Now, related to this idea of increasing and decreasing is the notion of positions on the graph where the graph is has a relative maximum or minimum point. For example, this is a maximum point for this graph. It's an absolute maximum actually, because there are no points above this point. So it is a maximum. This is the minimum point for this particular graph. Now when we get a particularly curvy situation, I don't see one over here. Stand by, I'm going to grab an eraser here. When the graph becomes more and more curvy, though, we have even more interesting things happen with this notion of maximum and minimum. For example, if I have a graph that looks like this, something like that, then I can say that the topmost point within a neighborhood right in here is called a relative maximum. Now, it's not an absolute maximum because there are vertical distances that are even higher than this over here and over here. But it's a relative maximum. Relative to its neighborhood, it's a maximum. And this is a minimum. Now, it's not an absolute minimum because there are distances below this point, you see over here, but it's a relative minimum. And here we have a relative maximum, another relative minimum, and this graph goes without bound upward here and downward here. But these are relative, we say relative extremes. You see relative maximum or minimum points. This function involves a rather peculiar notation, and the graph of the function is rather peculiar as well. This notation is the notation for greatest integer, so this would be read the greatest integer in x. Now, the interpretation of it can be explained by looking at a table of values. Suppose I wanted to plot some points. Now, the greatest integer in 1, when x is replaced with 1, the greatest integer in 1 is 1. The greatest integer in 1.3 is still 1. The greatest integer in 1.7, still 1. The greatest integer in 1.9, still 1. The greatest integer in 2, though, is 2. The greatest integer in 2.5 is 2. Okay, we get the idea here. Now, graphically, look at what happens. I've constructed the graph of these points. I've plotted these points. Now, for x values that are between 1 and 2, the greatest integer for all of those numbers is 1. So we have this graph. But once we get to 2, we are no longer here. We jump up to this point, you see. And for values of x that are between 2 and 3, the greatest integer in those numbers is 2 until we get to 3. And then we jump to 3. And then we go across like this, and this pattern kind of continues like this. So let's see. This is called a step function for perhaps obvious reasons here because of this stair-step affair with the graph. Kind of neat kind of function. And you might be thinking, gee, where is this ever useful? Well, it turns out that telephone bills are a lot of times described by using step functions. If your telephone charge is on the basis of a particular amount of money for, let's say, the first minute, and then a particular amount of money, a different amount, for every minute thereafter, well, what happens with parts of minutes? Well, it turns out that you're charged the greatest integer in the number of minutes that you talk. Here's what I mean. Suppose we're charged 50 cents for the first minute and 36 minutes for each additional minute. Now, where do parts of minutes come in? If you talk for 1 minute and 10 seconds, you're going to be charged 50 cents for that first minute, and that 10 seconds in that second minute kicks you over to an additional 36 cents. You see, and so let's write an equation for this, and it'll be a step function. It's a cost idea, or the cost of these telephone charges is, it's 50 cents is the fixed charge plus the greatest integer in an amount of time in minutes times 36 cents. You see, now, so for 0 to 1 minute, the greatest integer from 0 to 1 is 0. So for 30 seconds of time, you're charged nothing over here. You're in that first minute. That's that 50 cents idea. And for the next minute, once you jump over 1 minute, once you get to the 1 minute mark, then you're charged here. But like for 1.5 minutes, you've got 50 cents plus, let's see, 1.5 minutes right here. The greatest integer in 1.5 minutes is 1. So it's 1 times 36. You see, even though you're talking for only 1 minute and 30 seconds, you're charged for that as a whole minute. You see that additional minute. Anyway, that's the function associated with a telephone bill such as this. Kind of an interesting and weird situation. Functions can be classified according to even and odd. And the even and odd notion for functions is related to the idea of symmetry. Now, symmetry can occur in 3 different ways. Symmetry about the x-axis, y-axis, and origin. Here's an example of a graph which is symmetric to the y-axis. And symmetry is fundamentally the idea that we could fold along our line of symmetry, in this case the y-axis, and the graph would fold onto itself. Now, the equation related to this graph is y equals x squared minus 2. We can evaluate for y-axis symmetry by making a certain replacement within the equation. Now, that replacement can be evaluated, or we can understand the nature of it by understanding this folding idea. If this is a point xy that is on the graph, then notice that when we fold right onto a point which is negative x, y. So anytime a point xy is on the graph, a point negative x, y is on the graph. And so the evaluation algebraically involves taking the equation, replace x with negative x, and we should have an equivalent equation. All right, that's the notion. So we replace x with negative x, we evaluate, this becomes y equals x squared minus 2, oh happy day, it's the same thing we had before, so we determine that we have this y-axis symmetry. Now look at it in terms of function notation though. f of x is x squared minus 2. F of negative x, you see, what do we have right here? You see, this is, if we're talking about f of x for this, then when we replace x with negative x in the same function, this is really f of negative x. And f of negative x turns out to be the same thing as f of x. And if f of x is equal to f of negative x, then we have an even function. Then f of x is an even function. Now, here's how the evaluation would be made. I mean, we can evaluate like this, certainly using the equation format, but we should be able to use the function format as well. If we begin the notion like this, all right, here's our function. Here's how we think through it. And we'll go through many similar steps that we have over here. But you write that down, and now to evaluate for y-axis symmetry, we're trying to see if f of negative x is equal to that. Well, first of all, just make the substitution for f of negative x. This means in the f function, replace x with negative x. So this becomes negative x squared minus 2. You see, and now this becomes x squared minus 2. But x squared minus 2 is this, which is that. So this is f of x. So f of x is equal to f of negative x, and we determine then that f of x is even. All right, that's the idea. Now, symmetry also involves, or we can have symmetry about the x-axis. But if we have symmetry about the x-axis, we would have a graph that kind of looks like this. But this is not the graph of a function, so it doesn't fall into this even and odd evaluation notion. All right, so let's skip this. But just for completeness, I want to tell you that the notion of symmetry includes this x-axis symmetry, but it just doesn't fall into this evaluation for functions. All right, a third kind of symmetry is symmetry about the origin. Now, this kind of symmetry can be thought of as being a double fold kind of idea, where if you folded along the y-axis like this, you see, then you would get a graph that kind of looks like that. And then if you fold along the x-axis, just twist along the x-axis like this, boom, then it would imprint upon itself. So after that double folding occurs, then we have the proper imprint. Okay, that's the idea. Now, if we follow a point from one spot to another in this double folding process, then this is what it looks like. We take a point x, y, just an arbitrary point on the graph, and when we do the first fold, that rascal moves to, I shouldn't have erased that, that rascal moves to a point over here, and it is the point negative x, y, but we have another fold to go through. When we fold down this way, when we twist around this x-axis, boom, like this, that point moves down here. And now we have the same horizontal component that we had up here, but we have the negative of that y down here. So it turns out that when a point xy is on the graph, then the negative of x negative y is also on the graph. And that becomes the basis upon evaluation for symmetry about the origin. Now, if we're just looking at an equation, we make the evaluation by replacing y with negative y and x with negative x everywhere we see them. And then we manipulate a little bit. Well, let's see, this becomes negative x all cubed, negative x times negative x times negative x. That's the negative of x cubed. This is plus x. Now we would go through and try to make this look like that if we can. Multiply by negative 1, and we find y equals x cubed minus x. Oh, these do look alike, therefore we have symmetry about the origin. Now, in function notation, though, it works like this. That if this is, let me just show it to you right here and try to march through these steps. If this is f of x, all right, then look at this right here. This is replacing x with negative x. You see, is really f of negative x. All right, now, what is, let's see, let me rewrite this rascal. Oh, I'm going through maybe a little bit more than I wanted to here. All right, rather than have this minus sign, let me just write it the way I had it. All right, now let me force the factorization of a negative sign. The negative of x cubed minus x. But x cubed minus x is x cubed minus x. This is f of x. That's f of x. So this is nothing more than the negative of f of x. You see, kind of like that. All right, for emphasis, I'm putting the brackets in here. Okay, so we start with f of negative x. We manipulate to a point where we have the negative of f of x. And if it's the case that, and I'm using g here and f here, but it really doesn't make any difference. If g of negative x is equal to the negative of g of x, then g of x is odd. Same idea with f of x. If f of negative x is equal to the negative of f of x, then f of x is odd. All right. Now, here's how we would evaluate from the get-go. If we were starting out with f of x equals x cubed minus x, then we would begin by doing something like this. And we can start either way. That is, we can write f of negative x, or we can go from the negative of f of x and manipulate forward. But if I go f of negative x, then it means I just replace these with their negatives, like this. And now I want to manipulate into a particular form. And it's very similar to what I did over here. Negative x cubed plus x. And now I'm trying to create a situation where I have the negative of f of x, the negative of this. So I'll force that factorization here, and I get, and this then is the negative of f of x, and therefore I determine then, because f of negative x is equal to the negative of f of x, I determine that f of x is odd. Now, it's no idle coincidence that we have an odd function here, and it turns out that that exponent is odd, and this exponent is odd. You see, now, it's not always the case that just because we have odd exponents, we're going to have an odd function. But if we have an odd function, we will have odd exponents. I should say it that way. There are certain functions which have odd exponents which are not odd functions. That is, they don't represent this idea of symmetry about the origin. Now, in a similar way, let's move back over here and look at the exponents. We had an even function here, and the exponent here is even. Same idea.